Moissanite, the second hardest mineral. Moissanite is a naturally occurring mineral called silicon carbide, but it is so rare that it is almost never found in nature in large enough pieces to be cut into gemstones. For this reason, all of the moissanite used in jewelry is created in a laboratory. Moissanite was first discovered in a meteor crater in Arizona in 1893. Moissanite is the name given to naturally occurring silicon carbide and to its various crystalline polymorphs. Silicon carbide is useful for commercial and industrial applications due to its hardness, optical properties, and thermal conductivity. Mineral moissanite was discovered by Henri Moissan while examining rock samples from a meteor crater located in Canyon Diablo, Arizona, in 1893. At first, he mistakenly identified the crystals as diamonds, but in 1904 he identified the crystals as silicon carbide. The mineral was named in his honor. The mineral form of silicon carbide was named moissanite in honor of Moissan later on in his life. The discovery in the Canyon Diablo meteorite and other places was challenged for a long time as carborundum contamination from man-made abrasive tools. Natural moissanite formation. Natural moissanite, a captivating gemstone with exceptional brilliance, boasts a fascinating genesis rooted in the extreme environments of meteorites and Earth's mantle. Cosmic origins. Extraterrestrial birthplace. The majority of natural moissanite arrives on Earth within meteorites, celestial visitors formed from the remnants of supernovae or collisions between stars. These interstellar rocks, subjected to immense heat and pressure during their cosmic journeys, crystallize silicon carbide, SiC, into moissanite grains. Volcanic delights. Volcanic eruptions can occasionally bring moissanite to the surface. As molten rock, spewing from Earth's core, cools under specific conditions, rare moissanite formations can crystallize within the solidified magma. The precise formation conditions for Earth-born moissanite remain an active area of research. Scientists believe it requires an environment exceptionally low in oxygen and rich in carbon, coupled with extreme heat and pressure exceeding 1,200 degrees Celsius and 30 kilobars. Moissanite properties. 1. Composition. Silicon carbide, a naturally occurring mineral formed in meteorites or created in labs under high pressure and temperature. 2. Color. Typically colorless, but can also be found in shades of yellow, green, brown, and gray. 3. Luster. Adamantine to metallic, meaning it has a diamond-like brilliance with a hint of metallic sheen. 4. Crystal system, hexagonal, featuring six-sided pyramidal crystals and intricate formations. 5. Streak, greenish-gray, the color powder left behind when scratched. 6. Hardness, 9.25 on the Mohs scale, second only to diamond, 10, and incredibly resistant to scratches and wear. 7. Cleavage, none, meaning it doesn't break along specific planes like some gemstones. 8. Crystal form, typically found as single crystals or twins, with beautiful geometric shapes. 9. Density, 3.22 g/cm cubed, slightly less dense than diamond, 3.52 g/cm cubed. 10. Transparency, transparent, allowing light to pass through, enhancing its brilliance. 11. Fracture, conchoidal, meaning it breaks with smooth, curved surfaces like shells. 12. Specific gravity, 3.22, the ratio of its density to the density of water. 13. Solubility, insoluble in common acids and solvents, adding to its durability. 14. Magnetism, non-magnetic, not attracted to magnets. 15. Fluorescence, weak to moderate fluorescence under long-wave ultraviolet light, appearing blue or green. 16. Pleochroism, weak, meaning it shows slight variations in color depending on the viewing angle. 17. Refractive index, 2.65 to 2.69, a measure of how much light bends when passing through the stone, contributing to its intense fire. 18. Inclusions may contain needle-like inclusions or gas bubbles, especially in natural moissanite, adding a unique character. Synthetic moissanite. The creation of synthetic moissanite can be achieved through several scientific techniques, each offering distinct advantages and control over the final gemstone. Here's a closer look at 3 main methods. 1. Verneuil process. Mechanism. This traditional method utilizes a high-temperature oxyhydrogen flame to melt a mixture of silicon dioxide and carbon. Tiny droplets of molten material fall onto a seed crystal, gradually building up and solidifying into a moissanite boule. Advantages: relatively simple and cost-effective, suitable for creating larger crystals. Limitations: high potential for inclusion formation, limited control over crystal orientation and color. 2. Czochralski process. Mechanism: a crucible containing molten silicon carbide is heated, and a seed crystal is dipped into the melt. As the crystal is slowly pulled upwards and rotated, the molten silicon carbide solidifies onto it, growing a single crystal moissanite boule. Advantages: produces high-quality, inclusion-free crystals with superior optical properties and controlled crystal orientation. Limitations: slower growth rate compared to verneuil, higher equipment cost. 3. Chemical vapor deposition, CVD. Mechanism: precursor materials like silicon tetrachloride, Si, Cl, and methane, Ch, are vaporized and introduced into a vacuum chamber. Under carefully controlled temperature, pressure, and gas composition, the vapors react and deposit onto a substrate, forming a layer-by-layer moissanite film. Advantages: offers the most precise control over crystal structure, thickness, and dopant incorporation, enabling creation of custom colors and features like rainbow moissanite. Limitations: requires sophisticated equipment and high technical expertise, typically produces thinner films compared to other methods.